Okay, here we are. Core concept number 4. So we got work. We're going to build on that and see what work is all about and get some additional quantities that we derive from there and try and understand a few more concepts. And I'll just recap where we were. I talked about this mass m being subject to a force, as if I was pulling it to make it or to get it to move at the same velocity with which, let's say, I was walking. And if you remember that example, we computed that force and then we said, okay, it's going to take as many meters to reach that final velocity. We assumed it was at rest. I'm just going to state its initial velocity is u in time t seconds. We know acceleration is final velocity minus initial velocity times divided by time. Force is mass times acceleration. If the force that I applied was constant to get this object to its final velocity, then definitely acceleration is constant. And when acceleration is constant, we also know that average velocity, which is v plus u by 2, average velocity times t, gave me distance traveled. And I wrote this down because I'm going to do some creative work here with this equation, okay? So let's see what I have if I build this equation and go back to my formula for work, which is force times displacement, right? So I know my force is mass times acceleration, and I know acceleration can be written in this form. So if I did this, I would substitute this for acceleration and force, and for displacement, I would substitute this relationship. And let's see what that gives me. It would give me work done equal to mass times, I'm going to substitute acceleration here, not 2 but t time, and for displacement I'm going to write that as times t. Now if you know your mathematics, I can tell time cancels out, and then v minus u and v plus u, if you know your algebra, a minus b times a plus b is a square minus b square. This would become mass times v square minus u square by 2. So if you can see, my force that I applied for a period of time t resulted in something happening to this object. Its momentum, its core property of motion changed from m times u to m times v. I've transferred something from that effort I put in by way of that force. I have transferred that to the object, increasing that momentum, which now, if I come to the mathematics behind it, 1/2 of mass times, you'll have to excuse my, just so you don't confuse it with meters, v square minus 1/2 mass times u square. This represents the initial state, in which case this is the final state. That force and the resultant work done led to a transfer of energy, and this is where I'm using the word energy here. If this was the initial energy, and I'm going to call this, because it's moving, I'm going to call this kinetic energy, Ke initial, minus, this one would be kinetic energy final. So it's initial kinetic energy subtracted from the final kinetic energy which is the difference in the energy, is the work done by that force. So this effectively becomes what is called as the work energy principle, right? But I'm going to pause there and just quickly go back to this little creative algebra I did and touch on a formula that a lot of curriculum they probably teach this even before you get to high school, and I purposely didn't include this in Core Concepts 1 when I talked about all the different formulae, but let's just play with this a little bit. If you just multiply this, I just want to creatively play with this and show you what is going on here and what kind of derivation you can get out of this. All right, so let me just, let's say we start with let's just play with these two for the time being. Okay, we will say what's the best way to do this? I want you to intuit this formula. The reason I didn't include it initially is because most curricula try to teach people this as a formula. It really doesn't make sense. I mean, the reason why we want to represent the acceleration component and the displacement component in velocity terms becomes more evident here. But really what happened in this, if you notice, if I had these two equations and I multiplied them, just these two, what I would get is I could derive this as acceleration times displacement would be equal to, I think if my math is right, I would do this: velocity difference and velocity average. This would be T. If you see this, acceleration times displacement gives me that, which would really be, if I cancel that out, I could rewrite this as v square minus u square divided by 2, and this would be, rearranging this, I would write v square equal to u square plus 2as, or v square minus u square is equal to 2as. They call it the constant acceleration equation. Usually the derivation in this formula is kind of given to you when you study s is equal to ut plus half at squared and things like that, or v is equal to u plus at. So if you remember the equation, v is equal to u plus at, which is a more intuitive form of understanding final velocity, and you also know s is equal to ut plus half at squared. They usually teach you this in most textbooks at that same level where they teach you these two equations. I purposely did not do this. I wanted to bring it here because I want you to see that this is really what I call this the equation of convenience, because I do that really just to conveniently solve this mathematics. There isn't much I would intuit here in terms of squaring velocity, because at an early stage of learning mechanics, you really don't square velocity very much. But I thought I'd just go over this as a quick digression, just to cover that part. I'll take that off for now. But back to work, kinetic energy, final minus kinetic energy initial. Basically, work done by the force is really the energy that has been transferred into that object. A force acting on an object is said to do some work which is equal to the transfer of energy that has happened on that object, and that's the kinetic energy. And I'm calling it kinetic energy, just not energy, not just yet, right? And we'll get to that part in a second. I'll take all these things out. This was really just to help you digest the mathematics, the creative mathematics, if you will, that we just did. But what I want to do now is I want to just go back to, let's see if I can do this with, yeah, maybe just a piece of chalk, and that should do this. Okay, let's work with this. If you know this chalk has a mass, you also know mass of, let's say, m. We know that acceleration due to gravity is g, so that always exists. So if I'm holding this object at a particular height, and let me just say this is my base level, and I'm holding this object here, it's not making contact. There's the force that's acting, that my hand is exercising a force, and that's what's keeping this chalk here, because if it wasn't there, if there was no force, then gravitational force would basically pull it down. So if this chalk just stayed, and if this is the chalk, there's the gravitational force acting on it, which is really just m times g, which is a gravitational force. By me holding it up here, that means my hand is exerting a force F equal to, if mg is in this direction, negative m times g is the force and again, because I'm representing it as a vector, the negative is the direction, right? Its absolute value should be equal to mg. If you're with me on that, right? Now what happens if I lift it up here? So when I lifted it up here, there was force that was holding it, and then I'm lifting it up, and I drop it, so it comes down with a particular velocity. We know from the other example that if I dropped it, if I now lifted it up all the way here and dropped it, it didn't break this time, but if I did, at some point it would break. And we saw that in the previous example. This is obviously not going to break because the mass is lesser, I guess. But we learned that the higher the object was, the greater the impact we realized. That means it was traveling, and you know acceleration due to gravity, so as the height increases and you keep moving down, g keeps adding up every second. So after the first second, you have your velocity, which is say equal to g, right? As you come down, let's say t is 1 second here. After 2 seconds have passed, take another measure, your velocity will have increased, right? This time, because u plus at, this time your velocity will be 2g. Here, at this point, the right way is at this point, your velocity is 2g. As you came down, your velocity keeps increasing. And we know from that example that as we came down 1.2 meters, our final velocity was about 4.9 meters per second. If velocity keeps increasing, that means final kinetic energy is increasing. So if I fixed a base level, remember, if I fixed a base level, whatever that base level is, okay, this is my ground zero, if you will. As I lifted this higher up and it came down, it kept meeting the base level with higher and higher kinetic energy. So, but I was exerting work. More work done to bring this higher and higher up, but clearly no kinetic energy. But somehow there was kinetic energy, increasing kinetic energy. As I took this up, the kinetic energy that I felt here was much higher. So what was happening is somehow I was transferring, this work was transferring some kind of energy that then got translated into a higher kinetic energy. And that is why I will introduce something called potential energy, right? I will take this out. first thing I would do is in lifting something up by, let's say, a distance of h meters was the distance, the vertical distance, the vertical displacement was h meters. It was held with a force equal to mass times g. That vertical movement imparted work of mass times g times h. Now somehow this, as h increased, when I dropped it, kinetic energy, which was 0, ended up being much higher. There was a gravitational pull that created this, but that work done against gravity also contributed to some energy, because remember what I said, work is the transfer of energy. So what did I transfer as I moved up? I transferred something called potential energy. Until I released it, you were not able to see it in motion. Once motion happened, you observe that energy. That is the kinetic energy, the energy that is caused from motion. But otherwise, I was just building, increasing energy into it as I contributed, or my force did some work on it. I was increasing potential energy, right? And this work typically, in vertical movement, this work is increasing, and I'm drawing that, potential energy. When I dropped it all the way, kinetic energy, which was 0, came in here with a much higher kinetic energy. Effectively, all of the potential energy that was done got translated into kinetic energy. So as the object moved up through h meters, I did a work of, the work was m times g times h during this distance. When the object came here, suppose this is my base level, okay? This is the base level where potential energy was 0. And when I dropped it here, it came down here with an energy, its kinetic energy was 1/2, take that out, its mass times its velocity squared, the final velocity. Here, initial velocity was 0. So potential energy went up. When it was dropped, gravity brought it down. Force of gravity that acted on it, that force was constant because acceleration due to gravity is constant. The force is mg that acted on it. It worked, so the same force resulted in kinetic energy being at its maximum here, right? That was the maximum kinetic energy. And obviously you can calculate the final velocity very easily when you have the distance. We've seen that in the previous example. But what I want to illustrate here is the fact that there was something that happened, work was done, increasing its potential energy. When it came down, it was that potential energy that got converted to kinetic energy. So for every object, there is always, and I'm going to take all this out, there is always potential energy and when it's moving, it always has kinetic energy. The sum total of these two would be equal to its mechanical energy. Now you might say, hey, this object was moving horizontally, you didn't include any effect of gravity. Well, maybe it had some potential energy, we don't know that. We're only talking about the effect of this force in changing its kinetic energy. Whatever potential energy it had no other implication, because really that was only impacted in its vertical movement, which we didn't consider here. And here we only considered vertical movement. The potential energy was elevated, raised to a certain point, which was effectively the transfer of energy, which is potential energy going from zero to some value by the action of a force that my hand did, mg times h. That was the work done in transferring this energy. And then when I dropped it, there was gravitational force that brought it down and effectively took its initial kinetic energy was zero, but gave it full kinetic energy in the end, final kinetic energy through that equation. That would then give us, again, if you go back to that previous equation that I showed you, here is where you would go in and say, this would be, let's say, equal to 1/2, hopefully you can see this, mass times initial velocity was zero. That means what would I get here? I would get 2 times acceleration times distance. This 2 and this 2 cancels out. Distance here is h. Acceleration is nothing but g. mgh is the same work that I did in taking it up there. Hopefully you can see that energy is conserved. Right? And this really, the sum total of energy. So potential energy from zero goes to some value here. Kinetic energy is zero here. When dropped, it came back to a potential energy zero and a kinetic energy of mgh. So this work effectively would say, if I came up here, my potential energy would probably equal to mgh, and kinetic energy was zero, and as I came down, potential energy became zero and kinetic energy became mgh. So potential energy plus kinetic energy, mechanical energy, is always conserved. No other force other than gravity acting on an object, but mechanical energy is always conserved. Principle of conservation of energy. Okay? So I'm going to write that here. This is important. It's actually called conservation of mechanical energy. Means, what does it mean? It means mechanical energy, this would mean mechanical energy is unchanged in the absence of an external force. Other than gravity. This is the case where there was no other force other than gravity, right? Really, you would say, oh, there was some force in which you moved this F, but that was really just the reactive force of gravity. In the absence of gravity, I would not have had any force in moving this up. It would have just been a straightforward displacement. And in the absence of gravity, it would not have come down. So just stayed there. So in the absence of any force, if only gravity exists, then total mechanical energy is always unchanged. That's the conservation of mechanical energy. I'm not going to say conservation of energy because there's other types of energy. Heat, is an example, but this is just something for you to remember. Conservation of mechanical energy, right? So understand this. Kinetic energy and work, right? But understand that it's total mechanical energy that matters, because work is done even to alter potential energy. Gravitational force does work to alter kinetic energy. So effectively, you could say, if a force F acts on an object, then work is equal to the change in mechanical energy. If there was no force at all, and only gravity existed, there would be no change in mechanical energy. As soon as a force comes into being other than gravity, then that force does work, and that work is basically the transfer or the increase in mechanical energy. So if you go back to my first example, whatever be the potential energy of this, when it came in here, when you brought the box here, that potential energy may still continue as is, hasn't changed. Its kinetic energy changed, and that was the work which this force did. Now these problems will become really, really interesting when you start looking, or this concept of potential and kinetic energy will become really interesting if you start looking at an incline, and if you had a box that you were drawing up this incline, and you were pulling it up this way. Now suddenly things will change, and with gravity being present, gravity pulls it down here, which means you will resolve a component of gravity this way. So if this is theta, if the mass is m, gravitational force is m times g, that's gravitational force. It has a resolved component here. What do you think the angle would be? This angle would be right angle triangle. So if this is 90, what would that be? It's 90 minus theta, right? That would give you, yeah, it would be 90 minus theta. That would be the resolving force. You would use that angle. So you would get the cosine of that, which is really sine of theta. You'd get you'd resolve force due to gravity would get resolved here. Force due to gravity would have a component here, and then you would pull this way to keep this box. Assuming there was no friction, you would apply that force to hold this box here. And there, if you start moving the box, then you will understand what work done is and how potential and kinetic energy changes, because the higher you move it up the incline, the greater its potential energy, because it will want to speed down. And if you let go, it starts coming down with this force, but as it travels this distance, its velocity keeps increasing, and it'll have greater kinetic energy as it comes down to the ground. Hopefully this concept will become clear when we start looking at some problems, and if you start looking at some problems in your textbooks. But before we go into doing those problems, I am going to introduce the concept of friction, and then we'll start studying them, because it becomes more relevant when we add friction, so we actually know that if I was going to do some work to move an object, what those calculations would be. But we'll play with them a little bit later. But first I'm going to also leave you with another concept here. So we've looked at force. We know impulse is force times time, but we also know work done by a force is that force and the displacement, which we've translated to change in kinetic energy. But I'm also going to bring in another concept here, and that is the rate at which you would do the work, right? Think of it this way. I'm moving this up. Let's say I move it up by 50 centimeters or 0.5 meters, okay? But if I do it really fast, there is the difference. There's something has changed, right? In order to move it up, you just say if this was really heavy, and I was able to do that, versus if I was a bit weak, I'd probably go that way slowly. But if I was really strong, I'd go up. You'd say, wow, you'd say this guy is powerful. So think of the rate of doing work as power, right? So I'm going to define this term here, power. As the rate of doing work. Which was really power equal to work by time. Okay. Work by time. Now we will have problems where we are moving objects, and when we move something, we have displacement and we also have velocity. But what we're going to do here is just creatively, so this is one piece, but I'm also going to say if work is equal to force times displacement, I could write this as force times displacement divided by time. If anything is familiar, displacement over time equal to velocity. So I could also write power as force times velocity. Very, very useful when you have problems relating to vehicles, movement vehicles and things like that, where you say, okay, what's the power an engine has if it can generate a certain amount of force to keep a vehicle at a particular velocity. And obviously if you have friction and those forces, you know the object needs a particular force to keep it at that velocity because there's a constant force of drag or friction pulling it back. So therefore you will always have a force needed to keep something at that velocity, which means you can actually start computing the power of an engine. And power typically, and this is tricky, people would use I have to get another color. People would use a unit called watt, often denoted as W. That's why I was careful here not to write W is equal to F times S, because work is measured in joules, J, right? And we know that is joule, G-O-U-L-E, and that's watt. Again, creative work, when 1 joule for 1 second is 1 watt. So that's how the SI system is. The units are defined in such a way. But again, remember power in watts, and 1,000 watts is a kilowatt. So if you found, a certain amount of joules or Newton meters per second, then that would be, you would see kW, which is basically kilowatt of power. Okay, so I'll leave it there. Next concept, friction. When we get friction, I think it should be easier to start coming into doing these problems, because there will be constant friction that acts, and then we can start looking at problems where we have to look at the force and therefore the work done or the power required to overcome that friction, whether it's on a straight line or straight horizontal plane or an incline. And hopefully that will give us some more insights. But that's core concept 4. Really brought 2 concepts here. One is the work energy principle. I talked about the conservation of mechanical energy, talked about kinetic and potential energy and how they interact with each other, what work done means in terms of energy. Here it's kinetic energy, but work done effectively is the delta, work done by a force other than gravity is the total change of mechanical energy in an object, and then power is the rate at which work is done, and a derivative equation of power. So I'll leave you with those concepts. We'll see you in core concept 5, where we'll talk about friction, and then we'll start getting into a host of problems from different textbooks. I'll try and bring in as many as I can, and I might not use the board, I might use another means of conveying that, but so far, here we are. I think you should be all set to even start attempting some problems from most textbooks now, because you should have all the concepts here. If you meet friction, then wait till we pass that, but we'll do that very soon. Okay, good luck.